Hello and welcome. I'm Kapil Vaswani, and the topic of my talk today is about the high cost that all of us are paying by using garbage collection to get memory safety in high-level programming languages. And this is a cost that is high enough already, but it's going to get worse as we start using applications that need more and more memory and running on machines that have, for example, hundreds of gigabytes of memory, where garbage collection doesn't really scale. So what I'm going to propose is that we actually lose the garbage collector. So we exit the garbage collector, leave the garbage collector behind, and instead take control over memory management. And we are going to do this using very simple means by introducing very simple primitives to a safe language. And I claim that if we do this, then we can get both simplicity and safety, and we can get very high performance, potentially at an order of magnitude. And this is joint work with Piyus, Kedia, Manuel, Matt Parkinson, and Dimitrios from Microsoft Research, and Aaron Blankstein from Princeton University. Now, of course, not everything I've said is true, as goes without saying. But let's look at the problem first. Today, as developers, we have the choice of using either safe or unsafe languages for building our applications. So if you start with an unsafe language like C or C++, there is a potential that you can get very high performance. But you might inadvertently introduce vulnerabilities in your application which can lead to all sorts of exploits, and often do. On the other hand, you can start building your applications in a safe language like Java or .NET. But unfortunately, users of these applications written in these systems often complain about performance problems. And developers have to work really hard to get back all the performance that they've lost often because of garbage collection. For example, we've interacted with developers of Visual Studio who told us that when users are loading very large projects into Visual Studio, often Visual Studio doesn't respond well, and they had to explicitly switch off garbage collection at certain points, for example, when you start typing, so that the garbage collector doesn't introduce a lag, and you don't notice slow response times. Similarly, developers of other high-performance applications like ASP.NET and Hadoop, for example, often introduce custom memory allocators, often unsafe custom memory allocators, into their systems so that they can get back performance that they've lost, again, because of garbage collection. Now, this is not really an unknown new problem. There's been a lot of work in trying to bridge this gap between safe and high-performance systems. For example, there's a ton of work on trying to extend languages with abstractions such as ownership types, lifetimes, borrowing, regions, and so on, essentially to help programmers manage memory more explicitly in the context of a programming language. Now, these are nice abstractions, but as it turns out, when you apply these abstractions in practice, they tend out to be very complex and often very restrictive. For example, here's the type declaration of a parser in Rust that uses lifetimes and ownership to declare how memory is used by a parser. Now, you don't have to read this, but there's enough there to say that there's complexity which is very hard for most programmers because once you start defining the lifetime of all objects, it really does become very complicated. So what we claim is that a different approach to building systems that are both safe and high performance is in fact to start with a safe language like .NET or Java, a garbage collected language, keep all the safety checks, and remove garbage collection and replace it with safe manual memory management. And the claim here is that this is easier for programmers to use and gives you high performance. So I'll show you how this works. So what we are going to introduce is a very simple programming model. So we take a safe language and change the semantics of new to allocate memory in a manually managed heap instead of a garbage collected heap. And that we introduce delete that programmers can use to explicitly control and free objects as soon as they are no longer in use. So for example, here's a very simple example of an array class with a resize method where you're passing a new array and a new size. And the array resize method simply copies the objects over into a new array. And the programmer can allocate the new array using the new method and then use the delete construct to represent when the old array is no longer in use. But to get safety, what we introduce is a new exception in the language called a dangling reference exception. So this is an exception that is thrown if the programmer attempts to use an object that has previously been deleted. So this is what gives you safety. So note that it's a very simple programming language. Most C programmers are very familiar with this. There are no complex abstractions such as ownership types and so on. And most importantly, unlike C and C++, all errors result in exceptions. And they result in exceptions at the point you attempt to dereference using a dangling reference. And these exceptions can be caught and debugged fairly easily. So the real challenge of building a system like this is to build a system where you can efficiently detect dangling references. And in a way that's much faster than how it has been traditionally done. So our approach basically uses two key ideas. The first is we build an allocator that does not reuse virtual address space. So the allocator is going to try and give each object a unique address in the virtual address space, and it's not going to try and reuse that address as much as possible. And this exploits the fact that in large 64-bit systems, we have a lot of free very large virtual address spaces. In fact, we did some numbers and found that if you have applications that keep allocating objects, then it'll take at least a day for you to recycle the whole virtual address space. So we are not going to reuse virtual address space, and we are going to use paging hardware to detect when you try and dereference or use a dangling reference. So let me describe this in a little bit more detail. So we start out with a heap. Our allocator has a heap which is divided into generations. This is not to be confused with garbage collector generations. All objects get allocated in Gen 0 of all the segments of the heap. And this uses a very simple bump allocator, very similar to how a garbage collector works. So the allocation itself is very, very fast. Delete simply marks objects as being deleted, as having been freed. So delete actually does not do any reclamation. And periodically, the allocator is going to try and reclaim physical memory. Because now you have a heap where some of the objects are no longer have been deleted. The allocator is going to try and reuse physical memory, not virtual memory. And it does that by identifying pages, virtual pages in the address space that are causing these fragmentations where you have a lot of deleted objects, promoting all the live objects on these pages into the next generation, enabling protection on these virtual pages, and then reclaiming the underlying physical pages. Now, one of the things you might have noticed is that if you do all this, the objects in the virtual address space are still there. It's just that they are protected. So you can no longer access them. And that invalidates a whole bunch of references you might have to these objects. So what our system does is that it patches these invalid references lazily when you attempt to access one of these freed objects, and it resorts to eager patching in a GC style only when that's necessary. And finally, we will compact the heap when we start running out of the virtual address space, which in fact for most applications won't be necessary. But for long-running applications, you might have to compact the virtual address space once in a while. OK, so let's look at an example to see how this works. So let's consider the Gen 0 of a program executing at some point in time. Here, the gray objects, the boxes in gray represent allocated objects, and dotted lines represent pages in the address space. So now let's consider the first page where there's a single object that's been allocated. And the allocator receives a request to delete that object. And since this is the only object on that page, reclamation is very simple. We can actually reclaim physical memory right away. We simply enable protection on that page and reuse that and reclaim the underlying physical page. And then the allocator is free to reallocate this page to other virtual pages in the address space. So reclamation is very simple when all objects on a page get deleted. And it's actually very fast as well. As soon as the page goes away, as soon as you've deleted all objects on the page, the allocator can reuse that page for other objects in the address space. So you don't have to wait for a GC cycle for this to happen. Now, what happens if you have live objects on a page? So let's say that you receive a request to delete this object. In this case, there are still live objects on the page, but the allocator might decide at this point that the heap is fragmented enough that it needs to reclaim some of the physical memory. And at that point, it's going to go and copy these objects onto a page in Gen 1 and compact them in the process. And then it's able to reclaim the physical page underlying that virtual page. Now, what this does is that because you had live objects on that page, once you enable protection and reclaim the physical page, that page is no longer in use, which invalidates all the references to these live objects, both from the heap and from the stack. So to patch these references, we are not going to do a full GC trace, even in the lower generations. Instead, what we are going to do is a new approach called lazy patching. And the idea here is that we are going to patch these references only when you attempt to use a reference. So, and that's when an access violation is triggered, and our access violation handler is going to try and patch this reference. And the intuition here is that the working set of references that are actually used to reference live objects is usually very small, and you can fix it very quickly after you've done a little bit of promotion. And we are going to resort to scans of the heap only when lazy patching is very expensive. And to enable lazy patching, when the allocator is promoting live objects from one generation to the next, we are going to store some metadata in the form of a page table, a per segment page table, that's going to map where source objects, where target objects are placed for a given source object. And I'll describe this in the next slide. So let's see how patching works. So let's say, for example, you've migrated live objects away from a page into the next generation, and you have an invalid reference from the stack to that object that you follow, and you get and you try and follow. But before we migrate the objects away, we create an entry in what we call the remap table, where that is indexed using the source address of the page and contains the address of the target page where the objects have been placed. Now, when you get an exception, if you try and follow this reference, our allocator is able to look up into the remap table and patch this reference and point it to the right object on the stack, right object in the heap. And this happens as part of the exception handler. Now, the reason we are able to do this goes back to the reason why we chose a safe language as the design point, as the building block for this system. And it's because we are able to safely scan all the roots and identify what parts of the stack are references and what parts are values. And because we are able to identify references, we can go patch them. And this is harder to do if you start in an unsafe language. So what happens if you have a dangling reference? So if you have a reference to an object that has already been deleted and hasn't been copied over, you simply get an exception. The only difference between the delete in a C, C++ style language and a delete here is that not all dangling references, dereferences will generate an exception. You might have some dangling references that will point to objects that haven't yet been, the physical pages haven't yet been reclaimed, and they'll be just fine. But some, after the page has been reclaimed, the next dangling reference will actually generate an exception. So the exception semantics are slightly different. So the next thing I'm going to describe is how do we patch references from the heap. And it turns out in this case we use this observation that often when you get a reference because of a root, an element on the stack that's pointing to an invalid reference, the parent which points to the pointer to an object that's generating this reference often exists also in the root set. So in this case, for example, the parent is that object which is still live, and it contains a pointer to the heap. Now, when an object on the stack is dereferenced, the pointer to a parent still exists on the heap. So in that case, we will we simply do a shallow scan starting from the roots on the heap and go one level deep into the heap and try and find invalid references and patch all of them. So this is a very shallow scan, doesn't involve full tracing, but is able to patch references that are generated from the heap so that the next time you use the same parent object to load a reference onto the stack, it doesn't cause an exception anymore. Now, this patching of heap references is still a heuristic. And it turns out that it's not always the case that the parent that contains the reference is always on the stack. And that's where we introduce some compiler support to enable lazy patching. And the idea here is that the compiler is going to extend the lifetime of parents till a child is used to dereference an object. It's going to try and do that. And also there are cases where, in fact, you don't even have parent references. So let me give you an example of this operation, array of i.value. The compiler for this operation generates the following assembly code. So R2 contains the address of the array, and R3 contains the index, and 16 is the offset in the object that contains the where the array actually lives. Now, in this case, the parent object is array of I, and that the address of that parent never appears in the root. It's an implicit value that's computed during the move, but it actually never appears in the root set. So if the array was moved, then we are never able to patch this object. So to do this, to enable patching of in such cases, we change the compiler to generate slightly different code, where we use an extra register to capture the parent of the object. So in this case, for example, the address of the parent is explicitly computed into a register R4. And then if an exception occurs, the runtime can go and patch that root. It can follow the reference from R4 and patch the root. Note that this does use an extra register, but we've done a whole bunch of experiments using benchmarks, and we find that doing these transformations that keep parents alive or explicitly generate parents don't add a lot of runtime overhead to all of our benchmarks. The other thing that happens when you keep when you use lazy patching and don't patch all pointers eagerly and leave some of them invalid is that equality checking breaks. Now, equality checking is a core primitive in safe languages that allows you to take two references and tells you whether those references are equal or not. Now, because some of the references might be references to invalid references, to objects that have already been promoted, and some references are to promoted objects, you often get into the situation where if you do a bitwise comparison of two references, it won't give you the same result because the objects are in fact in different generations. So we've implemented a new logic for equality checking in safe languages that implements the correct semantics. It's aware of the fact that the objects might be in different generations. And it uses only 3 lookups in the common case where one of the object hasn't been promoted, one of the reference is to an object that hasn't been promoted, and the other reference is to an object that has been promoted. So that uses just 3 lookups. So like I mentioned, this notion of eager lazy patching works quite well when the working set of references that you use to index to reference live objects is very small. But there are cases where we have to resort to eager patching of the heap. And that's where we introduce this phase called a detangling phase. This is a concurrent background phase that is triggered only when the rate of page faults or access violation exceeds a certain threshold. And that's to detect scenarios where lazy patching is just not working, and it's not able to patch all the references in time. This is a phase that scans the heap and patches invalid references. Note that this is a phase which is much simpler and more efficient than tracing in a garbage collector, because the idea is that it's only a best effort phase. It tries to catch as many invalid references as possible, but it doesn't have to capture all of them, because in the worst case, we'll resort to lazy patching anyway. And also, it's a lot more cache-friendly and very easy to parallelize, because we know exactly where the deleted objects are. We don't have to trace to find deleted objects. And finally, we have this phase called compaction, which is triggered only when the application starts running out of virtual address space, and that happens very, very rarely. And this is a stop-the-world phase. It defragments the heap and relocates all the live objects from higher generations into a block in Gen 0, at the beginning of Gen 0 of the heap, and patches all the references. This does involve a very short stop-the-world window where all the threads are stopped, but most of the other phases of this compaction phase run completely concurrently with the mutators. Okay, so we've implemented this system in .NET Native, which is a production quality ahead-of-time compiler for .NET. The .NET Native runtime uses a background compacting collector, which is a fairly state-of-the-art collector, uses per-thread heaps, automatically adapts the size of the heap based on your allocation patterns, and it can run collections on each of the thread local heaps independently, so it doesn't have to block all the threads all the time. We've ported a whole bunch of .NET libraries and benchmarks to use delete, which was far more painstaking than we thought. These are benchmarks not written with a manual delete in mind. They are all written with a garbage collector in mind. And we've evaluated this system on a few benchmarks, and I'll talk about a couple of them. One of them is called GC Stress, which is a benchmark that was designed to stress the garbage collector, and it turns out also stresses our system. So this is a data parallel benchmark. And we chose this benchmark because we wanted to test the scalability of the memory allocator when you increase the number of threads. Each thread in this benchmark creates a tree, very large tree, makes passes over the tree, and randomly replaces objects in the tree. There's a parameter which you can control to stress different generations in the garbage collector. This parameter is the percentage of short-lived versus long-lived objects. So if you have more short-lived objects, there is more churn. And in the baseline on our garbage collector, this benchmark spends between 30 and 80% of the time doing garbage collection. So what I'm plotting here is the comparison between the execution time of this benchmark between GC and the manual mode. And it turns out that if you switch to manual mode and explicitly annotate deletes, you get a potential 3x improvement in performance. And what's interesting here is that the improvement in performance increases with the number of threads. So the garbage collection doesn't scale very well because of the number of times it has to stop the world, but our allocator has no stop the world phases, and therefore the scalability with threads is a lot better. We also notice a 2x improvement in the peak working set of this benchmark. So the working set goes down from over 10 gigabytes to around 5 gigabytes. And also we notice these improvements are higher when the number of short-lived objects is more, because there's more churn and the garbage collector has to run far more often. Just to give you an idea of how often the lazy patching occurs, in this benchmark we had, for 8 threads, the promotion phase was triggered thrice, which resulted in around 3 million page faults. And out of those 3 million page faults, around 80% of the time, we were able to find the parent that was causing these find the parent object and patch it on the heap. We also tested the system on real-world benchmarks. This is ASP.NET caching, which is a caching layer very commonly used in front of web servers to cache most commonly used database objects. Again, this is a highly concurrent benchmarks with lots of threads. And in this benchmark, we varied the size of the cache. So on the left is a cache with 1 million objects, and the right is a cache with 10 million objects. And we notice a 2x improvement in both in throughput and peak working set size. For example, with the 10 million, with the cache of size 10 million, throughput goes up from 0.2 million operations a second to 0.4 million operations a second. But what's also interesting to note is that the peak working set of this benchmark increases with the garbage collector as you increase the number of threads, which doesn't really make sense because the cache size is actually the same. But with our allocator, the peak working set is mostly more or less the same. And one of the other interesting aspects of this benchmark is that it has very low fragmentation, because objects that are often allocated together often die together. So you can reclaim all the objects together and reclaim the underlying physical pages without actually having to do a whole lot of work. So to conclude my talk, what we are proposing is a very simple memory model, programming model for memory management in safe languages. All we are doing is introducing the keyword delete and an exception that's thrown if you try and dereference a deleted object. We've built a high-performance memory allocator that backs this programming model. It exploits the fact that 64-bit machines have very large address spaces, and we don't have to reuse virtual address space eagerly. And we've shown up to 3x improvement in both throughput and peak working set in a number of benchmark applications. And we think this is a very key building block for safe and high-performance applications. And a number of other abstractions like ownership types and lifetimes can be built on top of this in a manner that's both safe and guarantees high performance. That's my talk, and I'm happy to take questions.
Thanks for your talk. Have you considered comparing with an actual GC, which does the same lazy trick as you're doing? So instead of updating all the reference in the existing heap, it will postpone it and do it later.
We don't know of garbage collectors that attempt this. I think what happens is that so there's this notion of if you don't patch the references, then equality checking, for example, breaks. So we don't know of systems that actually do this lazy patching.
So I'm trying to understand you're proposing a new programming model. And in your programming model, the garbage collector still has to go through your custom heap, because your custom heap can refer to the existing objects in the real heap.
Oh, so in this talk, I'm just describing a system that's completely independent, has no garbage collector.
Okay.
So there is no one going through our heap and trying to look for live objects.
Okay.
But that's an interesting future direction, to the idea that you can integrate a GC with a system that's manually managed like this.
Hi, great talk, thanks. Do you think it's possible to prove that If there's a dangling reference, then there will be, say if you're doing lazy patching, there will be an address in your remap table. Or if there is no dangling reference, there isn't also another address in the remap table. So basically...
So if there is a dangling reference and we don't find we can't map it to an object using our technique, then it's going to be a dangling reference to an object that has already been deleted. It's a reference to an object that has been deleted. And if we don't have a formal proof, but we think that we can show that if you find it, then it's the object that you were referring to to begin with.
So you think it's possible to prove that?
Yeah, I think it's possible to prove that, yes. We haven't done it formally, but I think it's possible to prove it.
I guess most of the garbage collection cost is coming from copying objects from one generation to the other. Have you thought about comparing against an automatic pre-tendering system that automatically allocates the objects in the right allocation so that you don't have the wrong promotion overhead?
To be honest, we haven't done that. We haven't compared with a pre-tendering collector yet. But it's true that most of the cost is actually coming from these objects going on to higher generation. But also there's a big cost of these objects staying there, even though as a programmer you know that they are no longer in use. And that increases the peak working set and reduces the how quickly you can reuse the address space.
Would you think performance is similar then to the manual system?
Sorry?
Would you think that performance of a runtime system that can do pre-tendering decisions very efficiently, effectively, that this performance would be similar then to your system?
I think we still have the benefit that we are using the programmer's knowledge that an object is no longer in use. And we can reclaim it as soon as the delete happens. A pre-tendering garbage collector will still have to wait till the higher generations, the right generation gets collected. And that can happen, quite far ahead in time.
So my question, hello.
Sorry.
My question relates to an earlier question. Why can't we be friends? To me, there's sort of two reasons why we like garbage collectors. One of them is, yes, our entire community is way too obsessed with soundness, and if it's not sound, then it's terribly wrong. I work in DOS. Soundness is, who cares about soundness? But the second reason is that manually deallocating things just sucks. We've all written these 100-line deinitializers that carefully go through the tree, and I need to deinitialize this, but actually this is a graph. If I've already deinitialized it there, I don't want to delete it here. There's these very, very intricate codes to do that. And it seems to me like there probably is just a huge portion of objects where, it's really obvious where to delete them. There's also a fair portion of objects where I don't want to, I just really don't. So is there something about adding a garbage collector to this system on the side that would sort of defeat the purpose, that running through the heap would defeat the benefits you gain, or do you think they're sort of orthogonal?
Well, I think this is there are many ways of actually making this kind of a system work together with a garbage collector. There's ways in which, for example, you can think of them as two separate heaps, one heap managed by the GC and one manually managed, and you can allow pointers across them, but the GC manages and all objects where, for example, deallocation is just too complicated, you could leave it up to the garbage collector and use this heap only for the real performance-sensitive scenarios where allocation is very heavy and you really want to reduce garbage collector pressure without having to write a custom allocator of your own. That's one way of integrating this with the GC. The other way of integrating this system with the GC is to think of it as the GC itself, but layer a mark phase on top of it, which goes and finds the objects that you want to delete, instead of you having to do it. So in that case, delete acts as a hint. So if you specify a delete, that's good. But if you don't specify it, the garbage collector will still go and collect it. So there's interesting work to do on sort of marrying these two systems.
Okay, so my question is... my question is about non-determinism, kind of, and debuggability.
Yes.
So it seems like there are some cases where whether or not you get a dangling reference exception is essentially random. So correct me if I'm wrong. For example, let's say I create a bunch of objects, then I create one object, delete it, and then reference it and never reference it again. So that would create a dangling reference exception only if that was the first object created on a new virtual page.
Yes.
Any ideas on like how to how to make this not a nightmare to debug?
Yeah. So there's the sort of delayed semantics of delete is a cost we are paying for getting high performance. It's what allows us to delay reclamation till some point in the future and batch it with other objects. But we've thought about, for example, modes in which you can run the same system in a debugging environment where you don't have to delay reclamation. And you can, in fact, get exceptions very early. So you could consider all sorts of modes where you can run the same system, but get exceptions at the point you do a dereference at a higher cost. But in production, whether you can do the same thing is an open question.
Great talk. Two questions. One of the reasons people prefer safe manual memory management is predictability. So you actually, at least from the presentation, it looks like you made you haven't addressed the predictability problem. And the second part of the question is, that one challenge in using page protection mechanisms, they come with a bag of overhead. So did you do anything special to reduce the overhead with page protection calls?
So predictability is a concern. We think that the system is far more predictable than a garbage collector because it doesn't have long pauses or doesn't have phases that actually scan the heap very often. I mean, there is detangling, which has to occur once in a while, but that only occurs if the lazy patching approach doesn't work. And lazy patching by itself doesn't introduce long pauses. So it's more predictable, but I wouldn't say it solves the predictability problem. And no, we haven't done anything special with the page protection mechanism. Although we could, for example, by using large pages, it's something we can benefit from, but we haven't done anything special with page protection.
So in your system, is it an error to delete the same object twice?
Yes, it is, and you get an exception for that too. Yes.
All right, quick question. I really enjoyed your talk. So we built a system a long time ago called Archipelago that also exploited the 64-bit thing. So it worked. It was great. We got great safety guarantees for C programs. But for some applications, we were killed by TLB misses. Why are you not getting killed by TLB misses?
That's a good question. We haven't investigated that enough yet. And my guess is that we are getting high TLB miss rates. But yeah, it doesn't seem to affect performance as much. I mean, we haven't done an evaluation where we've tried to optimize, for example, TLB misses and manage how pages are mapped. But it's an open question. I'm not completely sure why it's not killing us.
Is it possible that your applications are just not visiting memory enough?
Well, we have fairly large working sets. I mean, some of our applications are of the orders of tens to hundreds of gigabytes, and they are very frequently accessing. And some of these benchmarks are designed to stress test the allocator. So they are visiting a lot of pages and very frequently.
Okay, well, thank you very much, and see you back in a bit.